What are we trying to prove in our experiment? Our hypothesis is that there is a direct relationship between the mass of the balloon and the distance landed. We think the 100-gram balloons will go further than the 150 or the 200 grams. Our predictions conclude the Slingshot will not have enough energy to launch the water balloons with greater mass. When calculating the mass of the water balloons, we had to convert the units from milliliters to grams.
For our project, we're going to measure 4 different sizes of balloons. One is going to be 100 milliliters, one is going to be 150 milliliters, 200 milliliters, and 250 milliliters. And the way we're going to measure that is by water displacement of the balloons. So we're going to use this jar to see how much water each balloon displaces. So for this one, as you can see, it's almost exactly 100 milliliters. So that's 100 grams based on the conversion of milliliters to grams. And we're going to do that with each size of balloons, and if we need more or less, we're going to let out more water or less water until we have the perfect size of balloon to launch and test our hypothesis.
The setup we have with the Slingshot, we have two 4x4 posts planted into the ground. They're 32 inches apart and it's 5 feet tall. And so when we pull it back, we put increments in here, but we're going to fire each one at the 3-foot mark. This is at a 45-degree angle. Each time we fire it back, it'll be constant. When we fire, we're going to measure how far each one goes. And then we mark off the ground 10-foot increments with black spray paint. And it goes up to 150 feet. Now I'm going to explain how Slingshot works. It works by converting potential energy of the spring or the elastic, which is not perfect. It does not follow the 1/2 potential energy with 1/2 kx squared equation. So when you pull it back, you gradually increase the potential energy. And when you let go, the potential energy is slowly converted into kinetic energy until when the balloon is released and there's all kinetic energy, and then it fires. Experiment, we're going to do 3 different weights, 100 milliliters, 150 milliliters, and 200 milliliters. We were originally going to do 250 milliliters, but it popped when it was firing, so we're not going to do that. For the first trial, we're going to do 100 milliliters. So here it is. We're going to pull each trial back 3 feet. And then we're going to heavily seal apart. Trial 100 milliliter balloon. This black mark is 150 feet. So this one traveled 152 feet. This is the second trial for the 100 milliliter. Also fire at 3 feet. It's also very important to wear your safety glasses. This is the second trial for the 100 milliliter balloon. This is the 155-foot mark. And it went to 158 feet. Try 1 of the 150 milliliter balloon. First of 3 trials. About 126 feet and 9 inches. The 200 milliliter balloon, that right there is the 70 feet mark. And this is exactly 79 feet.
From our experiment, we concluded that there is a direct correlation between the weight of the projectile and the distance fired. The more massive the projectile is, the shorter distance it will be fired. The reason this correlation is true is because of the slingshot that was used in the experiment. The slingshot was not able to produce enough potential energy when it was pulled back to 3 feet at a 45 degrees angle to fire heavier projectiles. When analyzing the graphs, the relationship is very linear. The r-square values were extremely close to 1, which is a perfect best fit line. Also, with the equations produced from the graphs, the predicted distance fired of a certain mass can be calculated.